Hi everyone, welcome to our webinar today. The topic for this webinar is the market value of offshore wind on the US East Coast. This webinar is being presented by Clean Energy Group and the Clean Energy States Alliance on behalf of the Northeast Wind Resource Center. And our host for this webinar is Val Stori. Val is a project director at Clean Energy Group and the Clean Energy States Alliance. And we also have with us on the line our presenters who are from Lawrence Berkeley National Laboratory. Before I pass it over to all of those folks, I'd like to go over a few quick housekeeping notes. If you'd like to minimize your webinar console so that you can see the presentation full screen, you can use the little orange arrow that's circled here. You can also use that arrow to expand the webinar console. You have a couple of options to join the audio portion of the webinar. You can call in using a telephone, or you can use your computer mic and speakers. A very important note, we ask that you please submit your questions and your comments throughout the webinar by typing them into the questions box in the webinar console and hitting send. We'll get to as many questions as we can at the end of the webinar. We're going to save about 20 minutes for Q&A. So we'll get to as many questions as we can, but in order to make sure that we get to your question, please type it in when you think of it. Don't wait until the very end. And we're also doing something a little different today. We're having a Q&A just for members of the Clean Energy States Alliance. So if you've gotten an email from me or from Val with info about that, it should have included some login info. So that's directly after this webinar from 2 to 2:30 Eastern. So we hope to see you for that if you're a CISA member. And a final note, this portion of the webinar is being recorded. We'll send you a follow-up email probably this afternoon with a link to the recording and the slides, and we'll also be posting those on our website after the fact. And you can find that webinar archive at cleanegroup.org/webinars. So with all of that out of the way, I would like to pass it over to our host for today's webinar, Val Stori.
Great, thanks Sam, thanks Andrew, thanks Ryan, and thanks to everyone for joining us today. I'm very excited for this presentation and the Q&A session following it. This webinar is being brought to you by the Northeast Wind Resource Center, which is one of 5 DOE-funded wind resource centers in the U.S. It's funded in part by the U.S. Department of Energy's Wind Exchange Program. And the Northeast Wind Resource Center in particular serves the information needs of New England and New York for both land-based and offshore wind. And in the case of offshore wind, it also serves New Jersey. We provide information on wind energy, primarily to support policymakers at state, local, and regional levels, but also for the public at large. And in offshore wind, we work regionally in the Northeast and Mid-Atlantic on policy development, and we bring expertise and knowledge from others in the offshore wind arena and from Europe to share information with that group. So today as Sam said, we are having a presentation by Lawrence Berkeley National Lab. We have 2 of the report authors with us, Andrew Mills and Ryan Weiser, who will be talking about the report. This recently released report seeks to answer what the economic value of offshore wind projects would have been if they had been built if they had been in operation between 2007 and 2016. It took a look at actual wind data and wholesale prices along the East Coast and found wide variability in wholesale prices with implications for offshore wind. And their research, as you'll hear, suggests that the highest market values for offshore wind are in southern New England. And we'll learn more about their research and how the economic values for offshore wind was determined and the different values for the different locations. Let me introduce Ryan and Andrew. Andrew Mills is a research scientist in the Electricity Markets and Policy Group at LBNL. He conducts research on the integration of variable generation into the electric power system, evaluating the costs, benefits, and the institutional needs of renewable energy transmission and other supporting infrastructure. Andrew has a PhD in energy and resources from UC Berkeley and a BS in mechanical engineering from the Illinois Institute of Technology. And Ryan Weiser is a senior scientist in and group leader of the Electricity Markets and Policy Group at LBNL. He leads a research program that conducts analysis on renewable electricity systems, including on the costs, benefits, impacts, and market potential of renewable electricity sources, on electric grid operations and infrastructure impacts, on public acceptance and deployment barriers, and on the planning, design, and evaluation of renewable energy programs. He holds a BS in civil engineering from Stanford University and an MS and a PhD in energy and resources from the University of California, Berkeley. So with that, I'm going to turn the webinar over to Ryan and Andrew, and just give you all a reminder to please type in your questions into the question box. We have a hard end at 2 o'clock, so the sooner I get your questions, the more smoothly the post-presentation discussion can go. Thanks, everyone.
Great, and thanks, Val, and good morning or afternoon all. Thanks for joining today's webinar, again covering LBNL's recent analysis of the value of offshore wind along the east coast of the U.S. This is Ryan Weiser from LBL, and I'm going to be starting off the webinar today here with a pretty high-level overview of the motivation and a summary of the findings of the study. And I'm going to hand it off to my colleague, and he'll be Andrew Mills, who will be running through the majority of the slides, and will be taking you through, maybe not all, but a good subset of the gory details of our methods and findings. I'd like to start with a brief overview of the study. Sorry for the text-filled slide here, but in summary, the motivation here is pretty simple. As perhaps all of those on the webinar here, I'm sure can appreciate, offshore wind deployment is accelerating internationally, especially in the face of steeply reducing costs and low tender prices that we're observing in Europe. And of course, a considerable amount of interest in offshore wind also exists here in the US, with that interest growing both in depth and as well geographic reach over the last several years. That being said, in the US, the movement from interest to actual deployment has been a little bit slower, actually maybe considerably slower than in Europe, and perhaps in part due to an incomplete understanding of the economic value of offshore wind in local electricity markets. And with that context then, really the objective of our work was to develop a rigorous method to estimate the marginal value provided by offshore wind projects, focusing principally on economic value, but also including environmental impacts, and seeking wherever possible to fully consider how those values might vary by geographic location. More specifically, we do that by matching the characteristics of thousands of potential offshore wind sites up and down the eastern seaboard with relevant wholesale market and renewable energy certificate prices. And we do that for the period between 2007 to 2016, ultimately calculating not only energy value, capacity value, and REC value during that period, but also environmental outcomes, as well as price suppression effects for both natural gas and wholesale electricity prices. Now, it may seem a little bit strange for some of you that we're conducting this rather hypothetical and backwards-looking analysis of what the value of offshore wind would have been over the last decade or so. But I think it's important to recognize here that our goal was not really to identify precise estimates of going forward value, but instead to illustrate key value drivers and geographic results, while at the same time beginning to develop some of the methods that might be usefully used to benchmark future and more forward-looking assessments. And in fact, in executing the work, and in large measure what we hope to do was build on the large volume of work that has to this point emphasized in many instances the cost of offshore wind, with an equally robust, at least beginning discussion of a subset of the values that offshore wind might bring to the table. So with that as background, today's webinar is going to be structured as highlighted in this slide. And in particular, Andrew Mills will be really describing the meat of our work, describing the methods that we used, as well as the primary results, and covering those primary results not only as they relate to the historical value of offshore wind over that 2007 to 2016 period, but also how that value compares with land-based wind, as well as how the value of offshore wind might change in the future. In the underlying study, we also include some analysis of various ways in which the value of offshore wind might be increased through interconnection strategies, storage deployment, different offshore wind turbine technology options, and others. We're not going to have time to go through those results during the webinar, but we do have an appendix here with those supplemental results. Folks can certainly ask about them in the Q&A, and if you look at the presentation after the webinar, you can look through some of those results in more detail. Now, before turning it over to Andrew, I do want to provide a quick high-level verbal preview of some of the key findings that we'll be running through in more detail, and thankfully for all of you, with more graphics for the remainder of the hour. But specifically, some of our core findings are summarized both on this text-heavy slide and the following one. And let me summarize them briefly verbally here. First, we do find that the marginal total market value of offshore wind, considering energy capacity and renewable energy certificates, does vary significantly by project location, and at least in our analysis, tends to be highest for sites off of New York, Connecticut, Rhode Island, and Massachusetts. When we compare those value estimates with LCOE estimates, meanwhile, we find that the most attractive sites from that perspective tend to be located off of Massachusetts and Rhode Island, while the least attractive sites tend to be far offshore of Florida and Georgia. Third, in distinguishing the market value between different sites along the eastern seaboard, we find that the variations in value are driven primarily by differences in average energy and renewable energy certificate prices, and not really by differences in the underlying diurnal or seasonal wind generation profiles of different sites along that eastern seaboard. Fourth, and to be clear though, we do find that diurnal and seasonal generation profiles matter, but we find that those mostly matter for capacity value. And though, as Andrew will show, we do find that the capacity credit of offshore wind is rather attractive, especially in the northeastern region of the country. We also find that the monetary value of that capacity, at least on this historical basis, is rather small in comparison to energy value and renewable energy certificates. Fifth, we do find that the market value of offshore wind varies pretty significantly from year to year, with the lowest value year being the most recent year that we evaluated, the year 2016 in particular. Sixth, we find that the energy and capacity value of offshore wind does exceed the value of onshore wind, with those differences being caused both by the more attractive location of offshore wind, in effect, the ability of offshore wind to tie into constrained load pockets along the coastline. But we also find that the temporal output profile of offshore wind is more attractive than the temporal profile of land-based wind, especially in the northeastern and PJM regions. Seventh, we do find that offshore wind reduces air emissions that are harmful to human health and the environment, with those impacts varying over time and being largest in the mid-Atlantic region of the country, at least along that eastern seaboard. Eighth, some caveats do deserve note here, and Andrew will note some of them a little later. We find that the ability of offshore wind to reduce wholesale electricity and natural gas prices, that price suppression or merit order effects, are substantial. And finally, while we won't summarize these results in this presentation in the interest of time, they are in the appendix, and we do find that there are several means that might be used to further boost the value of offshore wind, including various interconnection strategies, selling renewable certificates at different states than the one in which the project interconnects, and finally, adding battery storage. So with that as a verbal and text-driven overview as a bit of a teaser, I'm now going to turn it over to Andrew Mills, who will take you through many of the details, both of our methods, as well as provide some more color on those basic findings. So off to you, Andrew.
Okay, great. Thank you, Ryan. And let's see if I have control of the slides here. There we go. So the first thing that we needed to do was to be able to estimate these historical wind profiles for these hypothetical offshore wind sites. And so this map here on the left shows all of the various wind sites that we considered. And the data for this came primarily from NREL's wind toolkit, which has a historical record of estimates of wind speeds at hub heights for all of these different sites that are shown here. We did do some screening of the wind toolkit sites to ensure that there was sort of a technical potential screen that was applied to ensure that we have adequate wind speed, that the water depth wasn't too deep, and that we're within the U.S. exclusive economic zone. That wind toolkit data set now extends over 2007 through 2013. And one of the things that we needed to do in this analysis in order to cover the full period that we were interested in was develop a method for extending that approach further all the way out in 2016. So one of the resources that's available is a more coarse analysis that's called the MERA data set, which is historical weather data. And what we did was that we used a downscaling method to be able to take that coarse MERA data from the more recent years and then associate that with what was produced at the wind toolkit sites on a site-by-site basis. And that helps to describe a relationship between what we see in the MERA data and these individual wind toolkit sites. And then based on those relationships, we could predict forward into the 2014, 2015, and 2016 years what the wind speeds would have been. And this analysis on the right-hand side just shows that when we did some comparisons that this downscaling method was fairly accurate and was able to reproduce the sort of diurnal patterns that are fairly important for this analysis with a high degree of accuracy. Once we have that wind speed data at each of these sites, we then convert that into the wind power that would be coming from these hypothetical offshore wind sites. And to do that, we used an offshore wind turbine power curve that is representative of a 6 megawatt turbine with 100-meter hub height, and then also has fairly large blades that are suitable for North American applications. So it leads to the specific wind power of 318 watts per meter squared. We then, once we have the wind speed through that individual wind turbine power curve, we then account for various different losses. So one of the main sources of losses that can occur is the fact that wind turbines are often arrayed in some sort of multiple turbine array, and you might have wake losses where you have interactions between those turbines. So we assumed for modeling wake losses that we would have a 10 by 10 grid of turbines. And then we have these wake losses are a function of speed, so that as you get up to very high speeds where the turbines are now at their rated power, those wake losses can actually go down. So wind speed was the only factor that we considered there. We also then have electrical losses to be able to transport that power from the offshore wind site then onto shore. And then we have various other losses associated with availability and curtailment. And there's a few other assumptions where we just kept air density constant over time and other things like that that have small effects on our estimates. And again, these maps here on the right now show what we end up with for the average wind speed at these various sites and the annual capacity factor that would have been predicted. Once we have the hourly wind generation profiles for all of those sites, the next thing to do is then to estimate these marginal benefits based on what the power system would have looked like during that same period, and to the degree that we can do that also on an hourly basis. And so from here, one of the things that we need to do is associate each of those individual wind sites with an actual pricing node in the electrical power system. And the way that we did this in this base results that we'll show here is that we just associated it with the nearest large pricing node. And then those pricing nodes are then located within one of the ISO capacity zones. And then we also have the individual ISO that they're associated with. For the REC values, we also associate them with individual states and assume that RECs are sold at that state level price. So the various things that we need to do then is once you have that hourly wind profile and you have the information about where it's interconnecting, is to start calculating these different value streams. So the first one is the energy value, which is based on just taking that hourly nodal real-time price at that particular location. This is also referred to as the locational marginal price. And so that's specific to each site and is reported on an hourly basis. We also then have the capacity value, which is based off of taking the wind generation profile and the methods that the ISO uses to calculate the capacity credit or the capacity contribution of the wind to its capacity market. And then also used the historical capacity prices. What was the ISO willing to pay for capacity in those historical years? And that's how we come up with our capacity value. The REC value is essentially just taking reported spot market monthly REC prices for tier 1 or class 1 RECs in each state, and then again our estimate of the monthly wind power. And then in order to do estimates of the avoided emissions, we used EPA's AVERT model. And this AVERT model estimates what generation would have been displaced for different profiles of generation resources. So we have that AVERT model for each of these historical years. We're able to run it with these wind profiles, estimate which generation would have been back down, and then what therefore would have been the avoided emissions from that. We also estimate, as Ryan mentioned, this wholesale price effect, which is the reduction in wholesale prices that then might be a benefit to consumers because of the lower price that they then purchase power at from the wholesale market. And to do this, we just had historical relationships between energy prices and demand, and we used that to essentially get a slope of the supply curve at different times and estimate the wholesale price effect. For natural gas price effect, we also have from the AVERT model how much natural gas burn was reduced, and then from that we have a price elasticity from EIA. We're able to estimate the reduction in natural gas prices that would have occurred from that reduction in natural gas demand. I think the important thing to just emphasize with all of this is that all of this analysis was done on this marginal basis, meaning that we're essentially estimating what the impact would have been of a small wind plant on the margin, but we don't account for what would be happening if you were to start to deploy large amounts of offshore wind. In order to do that, you'd have to think about what additional effects might occur as you add more and more wind. But this is just the first increment of offshore wind at each of these locations. One of the things to note is that the capacity markets in the East Coast do have varying ways that they treat capacity and the ways that they price that capacity. One of the biggest differences is that in ISO New England and New York ISO, there's both a summer and winter assessment period, whereas in PJM, it's just based on the summer. They also have differing times what they declare these peak periods to be. And they also have different ways of averaging what the production was over historical periods. So you have an offshore wind farm and it's got a historical production. You would then either use just in the New York ISO case, just what the production was during those peak periods for the previous year, or in some of the other cases, you'd be looking at averaging over multiple years. Finally, one other thing to note is that in the non-ISO regions outside of south of PJM, there are no wholesale capacity markets. And so in that case, in order to estimate this capacity value, we just simply assumed that the capacity credit rules that are used in PJM and the capacity prices from the southernmost region of PJM would be applied in that non-ISO region. One other thing to note is that in those regions, we also use, instead of hourly locational marginal prices, we only have something called the system lambda, which is a reflection of what the utilities report is their marginal cost of providing electricity. And in one particular case in South Carolina, we had a period where the system lambdas that were reported were quite high and much higher than some of their neighbors. And so that's going to affect our results you'll see in about the 2009 to 2013 period for South Carolina. Okay, and with that, just summarizes that we have these different value streams here that are shown in this bar that we're calculating. And those different value streams would be observed or sort of important to different actors in different ways. So if you take the capacity value, energy, and REC value and add that all together, that's essentially what the revenues might be for a merchant offshore wind plant if it were selling its power into these markets, or if you had an off-taker that was buying all of the power from that offshore wind plant, this is essentially their avoided cost. What don't they have to spend now because they're buying the offshore wind power rather than buying that power from the market? The wholesale value is essentially sort of the value to the system, which is just that a combination of capacity value and energy value. These natural gas price effects and wholesale price effects are instead those represent transfers to consumers in that they see a lower price of natural gas or electricity when they buy from the market, and that therefore lowers costs to consumers. There's also other values that might be important to decision makers that we didn't consider in this, and we just want to be clear that we have a fairly limited, narrow scope of what we're considering here. Finally, there's a few other limitations in the ways that we calculated these. So as I mentioned earlier, that there's just this, we're sort of doing this on the value on the margin, so we're not really considering what would happen as you were to deploy more and more offshore wind. We also don't account for the sort of very short-term variability or forecast errors associated with variable resources like offshore wind. And so we've seen studies that might estimate on the East Coast that those costs might add up to be somewhere in the $3 to $6 per megawatt hour for future studies that have looked at that. But we don't account for those in this. We also only account for transmission impacts through these locational marginal prices, but we don't look at incremental transmission needs or incremental potential deferral of transmission upgrade needs. Finally, our REC value to some degree reflects what you might think of as some of the environmental and health benefits of renewable resources and offshore wind in particular. But we don't do a full sort of cost accounting of the avoided costs due to the avoided emissions that we have. And other studies that have looked at that, particularly some work by Dev Milstein here, has shown that on the East Coast that those avoided health costs from reducing emissions from power plants can be quite substantial, from $26 a megawatt hour up to greater than $100 per megawatt hour, depending on the region and the methods that are used. Again, we don't directly calculate those benefits, but to some degree that might be reflected in the REC values that we see. Finally, when we're looking at the natural gas price effect and the wholesale price effect, we're just looking at the first year effects, and we're not considering how that might decay over time. And then in terms of the wholesale price effect, we're really looking at this at the system level, not really thinking about what might happen at individual locations, and we don't account for any sort of capacity market price suppression effect that might occur. And then finally, there are these other community or economic development impacts that we didn't directly consider in this analysis. Okay, from there, now I'll just get into the primary results, and I'll focus on these energy capacity and REC values and how that varies by location and over time. We'll look at some of the drivers of those values, and then compare that to onshore land-based wind, and then look at some of these other effects. So here, these maps show the energy capacity and REC value. The map on the left shows that averaged over this full 2007 to 2016 period at all of these individual sites that we looked at. And then in the right-hand map, it's the same scale, but only showing those values in 2016. One of the things that you see is that although the value is lower in 2016, the sort of geographic variation in value is similar between these two periods. And then in the 2007 to 2016 period, the median value for the sites around ISO New England, those New England states, is upwards of $110 per megawatt hour, and then going down towards the $55 per megawatt hour in the non-ISO region south of PJM. We'll see that the variation that we see from site to site here is primarily driven by the variation in average electricity and REC prices, rather than being primarily a function of the wind power profile and how that differs from site to site. And then the reason why the value is lower in 2016 is primarily, again, because wholesale prices and REC prices have gone lower in more recent years, and that's what's driven the overall value lower in more recent years. This chart now shows for each of those regions what the median site would be, the median value would be at these sites, and it breaks it down by those individual components. So you see in the blue bars is that capacity value, which is a small portion of the overall value over all years and all regions. And then the green bar is one of the largest, which is the energy value. It's the value for selling that electricity at the energy prices. And then the red bar is the REC value. And as was mentioned earlier, you can see that in most recent years that the value is lowest, but there's variation in the previous years depending on what the average electricity prices were in those years primarily. We also did this not just by the median site within each of those ISO regions, but we also associated our sites with the individual BOEM lease areas that have been identified. And so here we take those same results and we just find the average value for the sites within those different BOEM sites. And you can see that the sites that end up having the highest value over that historical period are some of those ones in the Massachusetts and Rhode Island area, along with New York. Again, you can see that South Carolina stands out here, but that's primarily due to that short window where we have very high system lambdas in that region relative to some of their neighboring states. So one of the questions that we had was what drives this variation that we see in value from across these different locations? And one of the things that we wanted to do was to try to tease out the effect of the wind profile from these other effects that might be due to just differences in average prices across different locations. So the way that we did that is that we calculated these normalized values, where essentially what we do is we take the value at an individual site and divide that by the value had that same amount of energy been produced with just a flat block of power. So just if it's been averaged over all hours and was consistently the same. And so that in effect takes the value of just that flat block and that variation away from the variation that's due to the profile. And so what we see in these maps now is just the variation from site to site that is due to differences in wind profile. And we can see that that overall variation is quite a bit smaller now when we're just looking at for the effects of profile. And the areas in yellow are those places where the profile is such that you would be more likely to be aligned with times of high value. And the darker purples are places where the profile is less aligned with times of high value. We can see that for the total value and for the energy value, that there isn't that much variation from site to site. Over the total range is fairly small. But on the other hand, if we go to this capacity value, we do see quite a bit of variation. And again, the places with the highest capacity value tend to be in the Northeast region off of Massachusetts. But there are some places also in the Southeast where you do see that high capacity value due to the profile effects. And one of the reasons why we see that is because of that high capacity credit that you would be getting. So in the individual ISOs, they have this method where they take your wind generation during peak periods and estimate your capacity credit, which is your contribution of your nameplate capacity towards the capacity market. And you can see in the summer that that's what's shown on the left here, that the capacity credits tend to range from about 25% to 35% of the nameplate capacity of the offshore wind. In those other areas that just have, they also have a winter period, you can see that the capacity credits are much higher in that winter period. So in the New England ISO case here, you can see that the assessment during the winter period can go upwards of above 60% capacity credit in the winter. And then New York is also quite high. In the PJM area, they only associate that based on the summer period. And then what we did next was we took those offshore wind sites, the median offshore wind sites, and compared those to what we would see for onshore wind sites. We have historical wind sites that for places where wind has already been developed on the East Coast. And we were interested in applying the same methods to try to estimate what the value of onshore wind is relative to the value that we're seeing for offshore wind. And here we have the ISOs report the aggregate wind profiles historically. So instead of using the wind toolkit data, we're now using the actual wind profiles reported by the ISOs for these different regions. And then again, we're doing the same thing where we're taking that hourly wind profile and then using that to calculate the energy value and capacity value in particular historical years. Now, one limitation of this is that we don't have that full 2007 to 2016 period covered with those actual wind profiles, but instead we only show this comparison for those periods where the ISOs report the aggregate profiles. And this map here on the right shows the location and size of the existing onshore wind sites as of the end of 2016. And so this chart now shows the comparison of the onshore and offshore wind sites. The onshore are the lighter bars, and the offshore wind sites that we've looked at earlier are the hashed or darker bars that you can see here. And we're comparing both the capacity value and the energy value from these sites. And you can see that consistently across all of the years and all of the regions, the value of the offshore wind was consistently higher than the value of onshore wind in the same region in the same year. One of the things that we were interested in trying to understand was how much of that difference between the value of the offshore sites versus the onshore sites is just due to the fact that offshore is located closer to load and where you might expect wholesale prices are somewhat higher. So that's sort of the locational difference versus differences being because onshore wind has a different wind generation profile from offshore wind. So these dots that you see on here represent the portion of the difference between onshore and offshore wind that's due to location. And so in the case of New York ISO for 2016, for example, that gap between the onshore and offshore wind sites, about 75% of that difference is due to the fact that offshore wind sites would be closer to the high-priced LMP nodes where the loads are greater. So 75% of that is due to location, and only 25% of that difference is due to the wind profiles being more favorable in the offshore wind sites. We can see that it tends to be that for the majority of cases, it is mostly due to location, but it does vary from year to year in terms of the relative contribution of those. So both profile and location matter for these differences between onshore wind and offshore wind. And one of the things that also varies between them is those capacity credits. We can see consistently that the offshore wind has a higher capacity credit both in the summer and in the winter period than what we would see for the onshore. These differences are pretty large, but again, because the capacity value makes up a fairly small portion of the total value, the relative difference between onshore and offshore wasn't as large as the capacity credit differences are. Finally, one of the things that we wanted to do was to be able to account for both the fact that we have differences in value, but we also have differences in costs between these different sites. So NREL has done a lot of work looking at the cost of offshore wind and how that varies with site and wind speed and distance from shore and factors like that. So we took our results, which are the total value of these different offshore wind sites, and then we took NREL estimates of the cost of those different wind sites, and we just took the difference between those two. And so we have the value net of the LCOE, and this is a method for us to be able to compare these individual sites to think of which is the most overall economically attractive, and it's a way to sort of rank these different sites. And we see that the sites that are most economically attractive from this metric are those that are in that Massachusetts, Rhode Island, and Connecticut, New York region where you see the most yellows. The sites that are the least attractive from this perspective because they have low value and high costs are those down in the Florida area and Georgia area where you're far off of shore. We wouldn't recommend necessarily using the absolute numbers here as something that's important because we're comparing historical values over a particular period to future cost estimates on a levelized basis. And so that's not quite the fair comparison for really getting a sense of the net costs. In order to do that, you'd want to compare both future projections of value to these future projections of costs. But here, this is at least useful for getting a relative ranking of these individual sites. So finally, we also took these same profiles and then through that AVERT model, went ahead and estimated what would be the displaced generation from these offshore wind sites and how does that vary by location. And you can see here that when the offshore wind is displacing the marginal generator, that in the southeast area, you can see about half of the generation that's being displaced is gas and about half of it is coal, whereas in the mid-Atlantic area, the majority of it is coal that's being displaced with a smaller portion of gas. And whereas in the Northeast, it's primarily gas that's being displaced with a small portion of coal. In the Northeast, you also see a fair amount of oil displacement that would occur, along with some other resources. Now, that displaced generation also means that we're avoiding some emissions. So this, the same AVERT model can now tell you what was the avoided emissions rate based on that avoided generation. And this shows the results over that historical period, both in terms of we have avoided SO2 in the top left, avoided NOx, avoided PM 2.5 in the bottom left, and then avoided CO2 in the bottom right. And depending on what generation was displaced and how emitting that generation is, you'll get these different avoided emission rates. And you can see that SO2 has declined over time as the air emissions rules have cleaned up some of the generation that's being displaced, and so that we're now displacing generation that's increasingly getting cleaner and cleaner over time. That is shown up most in SO2. You don't see that as much in CO2, but you do see a small trend there also. Again, we don't necessarily try to then take these avoided emission rates and calculate an economic benefit of that, but there are studies that have been done that showed that these values can be quite substantial. There we have the wholesale electricity price effect, also varies by location, and these can be quite substantial. We have, in this case, what we're doing is we're looking at how offshore wind would lower wholesale prices and therefore lower the cost to consumers who are purchasing power at that time. So here we're only accounting for power that might be purchased at spot market prices. And we assume that that's going to be a larger fraction in regions where there's these ISO markets, and will be a smaller fraction in the non-ISO regions in the southeast. That partly explains why we have these big regional differences. The other factor is just the size of the market that's being affected and the slope of the supply curve at times when offshore wind is being produced. We see that these values can be somewhere on the order of $25 to $35 per megawatt hour in the ISO regions. We also, using that information about the displaced natural gas, can estimate what the benefit would be to consumers who now are potentially facing a lower natural gas price across all of their end uses of natural gas. And so again, we take the AVERT model to estimate the avoided natural gas, and then we have EIA estimates of the elasticity of natural gas prices. The orange bars here show that that benefit to consumers looking at the entire U.S., including all end uses of natural gas, whereas in the blue bars, we're just looking at the benefit to consumers within the region where the offshore wind would be interconnecting. And you can see it's a much smaller fraction when you're only looking at the within region benefits. And then this slide summarizes all of those results, where we take for the median sites over that period of 2007 to 2016 and look at that, stacking up all these different value streams. And again, the thing to take away from this is that we do see quite a bit of variation from region to region, and that the energy value and the REC value are some of the highest value streams, whereas the capacity value is the smallest. These natural gas price effects and wholesale price effects can also be quite substantial. Finally, we'll just wrap up here with looking at an assessment of future trends. So this was all a historical look, but we can also look forward and think about how these different drivers of the value of offshore wind might be changing in the future. So the first is to look at energy value. And one of the things that we know has affected wholesale prices historically has been the price of natural gas, which is often a resource that's on the margin and setting electricity prices. And one of the things that we see is that that natural gas price estimates going forward are from EIA, that there's some increase in that, but that NYMEX futures show pretty flat over time. There's quite a bit of uncertainty in what those prices might be, which is shown by the bands around these central estimates. We also have a number of sites that, a number of studies that have projected future electricity prices across these different regions. And the majority of them show that estimates are that prices will increase from the lows that we've seen in 2016 going forward, but that increase might vary from region to region. One of the things to consider is that the capacity prices also historically have been quite low, but then in some of these estimates for future projections, the capacity prices do rise substantially. And so there might be an increase in the capacity value going forward, but a counteracting trend is that some of the ISO market rules have started to tighten their requirements for resources to qualify for capacity revenues, and so that might affect the value for offshore wind going forward. Studies have also projected REC values going forward, and we can see that in particularly in the Northeast, a lot of the projections are that REC prices will continue to decline over time, and so that as a source of revenue will decline. But there are some activities where there's separate offshore REC prices that have been or contracts that have been discussed and announced in some cases, and that might be a future source of revenue for offshore wind. Finally, for air emissions, again, we've seen that the avoided air emissions rates have gone down over time from 2007 to 2016, and primarily that's due to increasing regulations such as the MATS requirements that requires SO2 control technology at all power plants. We've also seen that the low natural gas prices have switched to some degree between coal and gas being on the margin, and then one of the things to think about going forward is whether emissions will continue to remain at these low levels as long as those regulations stay in place. The effect of natural gas prices is harder to predict because higher natural gas prices might encourage more coal into the entry into the markets, but then also it depends on where natural gas is on the stack and which resources are being displaced. Finally, the outlook for the electric and gas price effects is that one of the things to note is that what we've looked at here is just the first year effects, and that as resources are added, that we expect that effect might decay or moderate over time. But then there's also a lot of factors that might affect the overall elasticity of prices and how they respond to additional resources coming on. Again, natural gas prices might play a considerable role here in the outlook for that. Okay, and with that, I wanted to just end with providing our contact information if you wanted to follow up with any questions. And then from there, we'll take questions from Val.
Great. Thanks, Andrew. Thanks, Ryan. Don't forget to type in your questions if you have any. We have a few, so we can jump in. Can you revisit why the market value decreases over time? I believe that was earlier on in your presentation.
Yeah, the majority of the reason why we've seen the market value decrease over time has been the lower wholesale prices over time. So that we saw the highest prices in wholesale prices in say 2000, 2007, 2008 period. Also in the sort of 2012 to 2014 period. But those prices have declined over time to some degree as natural gas prices have declined, which has lowered wholesale prices. And then also as renewable resources have gotten somewhat less expensive, that has caused the REC value prices to decline over time. So our average over the 2007 to 2016 period is higher than what we saw in 2016, where those factors were led to the lowest prices.
Thanks. And what was the assumed size of your offshore wind increments?
So in this, we were just looking at the value on the margin. So the size wasn't actually that much of a factor in there. We're just sort of saying what would be the value of that first increment of it. But in order to do those modeling exercises, we did have to make some assumptions about like for the ray effects, for example, the wake effects. And in that case, what we did was that we were assuming it was 6 megawatt turbines that were arrayed in a 10 by 10 grid. So that would sort of represent the wake losses of a 600 megawatt offshore wind facility.
Okay, so would tech advancements such as larger turbines have any effect on your analysis or on market value?
So we did do some supplementary analysis. So that's one of the things that you can find in our more detailed results, is that we did look at what would happen when we go to potentially future wind turbines that are even larger, and we estimated what the value impacts would be. And what we saw was that they were very moderate, very small, that the overall estimate of the dollars per megawatt hour value was very similar to what we saw here for our 6 megawatt turbines. So we don't expect that would affect the market value to much degree, but what it might do is lower the overall cost side. So we think it has a bigger effect on the cost than it does on the value.
Okay. Let's see. We have a question specifically about slide 26, if that's net or cost. I don't know if Sam, you could pull out.
Yeah, yep. Slide 26. So this is just the total market value that we see here. So this is what you, in our value net of cost, you would compare these bars, the value here, to that cost to come up with that ranking. But this is just the value.
Okay. In your AVERT modeling, did you consider, when you're calculating avoided air emissions, did you consider vessel emissions associated with offshore wind?
No, so the AVERT model and the emissions that we're looking at is only considering the impact of the electricity generated from the offshore wind on the emissions of the other generation in the power system. So in order to come up with a total net avoided emissions, you would have to, as you mentioned, estimate what those vessel emissions would be, but that's not something that the AVERT model would be able to inform you on. So you could take the avoided emissions from AVERT and then compare it to some other estimates of the vessel emissions.
Okay. And did you look at annual capacity factors among the different offshore wind sites and the different onshore sites, or was it just offshore versus onshore?
So we did have representation of what the capacity factor would have been both for offshore and onshore wind sites in those particular historical years. That then is basically used to generate our hourly profile of offshore wind versus onshore wind. And that's where we then go through and calculate the relative value of those. The capacity factor also would factor into estimates of the difference in cost of those two, that you might have higher capacity factors of offshore wind because the wind speeds out there tend to be higher. So that's something when you're calculating the levelized cost, you also would want to account for that capacity factor of offshore wind versus onshore wind.
Great. And can you, I'm not sure if you mentioned, can you remind us the annual capacity factors you assumed for offshore and onshore?
Let me just jump to, so this is, Sam, if you want to jump to slide 8. So what we have here is the capacity factors that we estimated of these different sites. And this is just showing the 2016. Again, we end up with a capacity profile or a generation profile for each year. But in 2016, it ranged from somewhere on about 50% in some of the highest wind speed sites off of Massachusetts, down into the slightly below 30% for those sites off of Florida. Now, in terms of the capacity factor for the onshore wind sites, I don't have those numbers offhand. I'm not sure what they were, but they were somewhat lower because of the lower wind speeds for onshore wind sites.
Thank you. And in some cases, was the land-based wind more valuable? So, for example, when you were considering offshore wind incremental in value to land-based wind for location and generation profile, were you always looking at both, or was land-based wind ever more valuable when considering only one of those factors?
So the only thing that we compared for the onshore and offshore wind in this case was the value of them in terms of essentially it's our estimate of that wholesale value, the capacity and energy value. So we calculated that both for the onshore and offshore sites, and we found that those values were consistently higher for offshore wind than onshore wind across all years that we saw. What we didn't do was compare the offshore wind value net of offshore wind costs to the onshore wind value net of onshore wind costs. And historically, what we've seen is that onshore wind costs have been considerably lower than what we've seen for recent estimates or announced PPA prices for offshore wind. And so if you do that total value net of cost comparison, you would probably find, we didn't do this in our analysis, but you would probably find with this historical period that it would be the total value net of costs would be less attractive for the offshore wind sites than the onshore wind sites. Now, as you go out into the future and you think about offshore wind cost reduction potential, that answer might start to change. And also, if you think about potential constraints on the power system for adding more offshore wind, or not just constraints on the power system, but other constraints that might restrict the ability to develop more offshore wind, or onshore wind might also push you towards doing more offshore wind.
Right, so locational value here doesn't include the location of transmission, for example.
Well, yeah, to the degree that it's reflected in the LMPs, that locational value of transmission is to some degree why we see the higher value of offshore wind. And that's why we see that higher value. Now, what it doesn't account for is there a potential need to add more transmission to even be able to integrate more into the system? And that's the part where we didn't go that far into it. We were only looking at sort of what the LMPs reflect in terms of transmission costs.
Great. Okay, I think we have time for one more question. And someone has asked, you compared offshore wind mainly to fossil fuel resources. Does the presence of nuclear plants have an effect on your estimates?
The presence of nuclear plants can have an effect on the estimates, and that's to the degree that because we have nuclear plants that are providing electricity, that shifts out the supply curve. And had you not had those electricity prices, then the supply curve would be shifted in, and suddenly electricity prices would go higher. So if you didn't have the nuclear plants, we would expect higher electricity prices, and therefore a higher value of offshore wind compared to that. So to some degree, because of nuclear plants, we have these lower wholesale prices. And in particular, when you have low demand and you have a lot of supply like nuclear prices, that's going to lower the wholesale prices quite a bit, and reflects times where you might have very low prices approaching down towards even near zero prices at those times when load is very low and wind is generating quite a bit.
Great, thank you. I think we will leave it there so we can wrap this up. Sam, if you want to put up any of the last slides so folks have Ryan and Andrew's email address or our email address. If anyone has follow-up questions, that would be great. Thanks to everyone for joining us. Ryan and Andrew, thank you for presenting a very impressive study. I hope it's been useful to everyone. And we'll talk to you all soon. Thank you.